Hello everybody, I hope you're as excited as I am. It's Root Beer here, and we're looking at the last question on the 2003 Euclid. That's right, it's question number 10, and this should prove a bit of a challenge. So let's grab our pens, get our minds focused, and let's have a look here. A positive integer n is called savage if the integers from 1 up to n can be partitioned into three sets, A, B, and C, that satisfy these four conditions here. The sum of the elements in each of A, B, and C is the same. Okay, so immediately that tells me, without reading any more of this, that we have to be able to add up the numbers from 1 up to n and have that be divisible by 3. Okay, so already I think that sort of limits what n can be. N's got to be a multiple of 3 or one less than a multiple of 3. Interesting stuff. And I'll explain that a bit later if we're required to. A contains only odd numbers. B contains only even numbers. Now, the sum of the elements being the same, B is going to have an even sum. So that means A is going to have to contain an even number of odd numbers. So that's another thing I can conclude, because there's no way to add up an odd number of odd numbers and get an even sum. But it has to be even, because B's sum will be even. And finally, C contains every multiple of 3 and possibly other numbers. Okay. So those are some interesting conditions. We got 3 parts here. With question 10 can be quite challenging, as can question 9, along with, so nowadays they also have the Canadian Senior Mathematics Contest. The senior contest has a B part, and it's got B1, B2, B3. B3 on that can be quite challenging as well, in some cases harder than question 10 on the Euclid. So with these really hard questions, I recommend that if it's in multiple parts, which it almost always is, you read all the parts together, because you only have so much time to sort of read the question, discover, and investigate and everything like that, and then you got to write up your solution. So it's a good idea to read all the parts to see where exactly are they going with this. Should I do part A in a certain way as I'm investigating it in order to better understand how to put together part C? Okay, so these are things you keep in mind, and they can help keep the amount of time it takes you to do a question down. Okay, so I'm going to read all parts together, and then we're just going to focus on A and then B and then C probably. A, show that 8 is a savage integer. This is just going to get us comfortable with the concept of what a savage integer is, and it'll sort of give us an actual number that we can work with. B, prove that if n is an even savage integer, then n plus 4 over 12 is an integer. Okay. So it'll probably be some sort of counting argument there, I'm guessing. And C, determine all even savage integers less than 100. So with that, I bet we'd probably use B to narrow it down, and then maybe some of the stuff we learned in A and B to actually work out which of the numbers they can be. We're looking for all even savage integers, and B talks about even savage integers have to satisfy this. So assuming B is true, which it has to be, they asked us to prove it, we can actually give a short list for C right away. But let's not. Let's focus on A right now. We're going to see if we can understand savage integers a little better. So, I've got the numbers 1, 2, 3, 4, 5, 6, 7, and 8 here. And let's partition them into our odds and our evens. So our odds 1, 3, 5, 7. Our evens are 2, 4, 6, and 8. So only these possible numbers might go into B, only these numbers might go into A. And of course there is C, which has to have our multiples of 3 in here, 3 and 6. Okay. So we know the sums. We have to explain what we're doing, by the way, because every single part here is written. I think nowadays they usually make A still a light bulb question, but this was written, so we got to explain it. We know the sums of A, B, and C are the same, and add up to 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8, and that's going to be 36. Yeah. So in general, and this is probably going to be useful for this question, figuring out what the sum of A, sum of B, and sum of C should be. In general, the formula for the sum of the numbers 1 to n is n times n plus 1 over 2. This is a nice fact that you should make yourself comfortable with. I've talked about it in some of the other videos, although I can't really pick out which ones. But this is a nice result. There's a good proof for it. I might talk about it in the future at some point. In just a video dedicated to that stuff. But this is a great way to do the sum of integers from 1 up to n. So for 8, it would be 8 times 9 over 2, so that'd be 4 times 9, 36. So the sum of A is 12, sum of B is 12, and sum of C is 12. Okay, so C's got 3 and 6 in it. That's a sum of 9 already. In order to make a sum of 12, we need to have 3 more. Now we can't just add in the number 3, we've already got it, so the only way to do that is to actually add in 1 and 2. Okay. And if we were to do that, if 1's off our list, 3's off our list, 6 is off our list, 2 is off our list, A would be 4 and 8, A would be 5 and 7, B would be 4 and 8. Okay. But we need to explain this, so we're just going to go ahead and do that. C must contain 3 and 6, and add to 12. This leaves 3, 12 minus 6 minus 3, to add into C. This can only be done with 1 and 2. So C must be 1, 2, 3, and 6. Okay. So we performed our calculation. We said these things have to be in C, but C isn't quite topped up yet. So there's 3 remaining that we need to add to C in order to get that sum of 12. What can we do? What can we take from our odds and our evens and bring them all together? Okay? And in this case, there's only one possibility. We have to take the 1 and the 2. That's the only other way to get a sum of 3. I imagine for other savage numbers, there might be other ways to take these couple odd ones and these couple even ones and come together, and there'll be more of a choice, and it'll be harder to then ensure that the resulting A and B that are left have the right sum. So I think the question will get harder. But right now it has to be 1 and 2, and we've explained that. This leaves A with 5, 7, and B 3, 8. All have a sum of 12. So 8 is indeed savage, as they have called it. Okay. So there we've explained how 8 is savage. So B part. Prove that if n is an even savage integer, then n plus 4 over 12 is an integer. Okay. And so basically that means an even savage integer is 4 more than a multiple of 12. Now, how might we do that? So I've already said that n or n plus 1 has to be a multiple of 3. And the reason for that is if n were savage, then The sum of all the numbers would be n times n plus 1 over 2, but that needs to be split evenly amongst a, b, and c, so this has to be a multiple of 3. So that means either n or n plus 1 is a multiple of 3, because 3 is prime. And so that would certainly help us. It's an even number, so either we're looking at n being something like 6k, which is possible, or n would be like 2k and n plus 1 would be a multiple of 3, and there should be some way to work that out. So obviously n can't be a multiple of 6, so that's out right away. Because there's got to be some way to exclude that, because n being a multiple of 6 would not be a multiple of 12 plus 4. That doesn't work out. Okay, well, I'm going to write down what I do know. Suppose n, and we'll write it as 2k because we know it's supposed to be even, is savage. So then the sums of what a, b, and c, they've all got to be equal. They've got to be this sum all divided by 3. But that is n times n plus 1 over 2 all over 3 is n times n plus 1 over 6. Okay. Now n is 2k. So that's 2k times n times 2k plus 1. We'll talk about that in a moment. Over 6. And we can reduce that to k times 2k plus 1 all over 3. Okay. So that's got to be the sum. So for 8, k would have been 4, and we'd be looking at a sum of 4 times 9 over 3, which would have been, again, 3. All right. Sorry, would have been 12. 4 times 9 over 3 is 12. What else is there to do? So 3 needs to divide k times 3k plus 1. Since 3 is prime, either 3 divides k or 3 divides 2k plus 1. Okay. So I think if 3 divides k, we'll have sort of too many multiples of 3, and then c will be too large. That's my guess. So suppose 3 divides k. We'll say that k is equal to 3 p. Okay. That way, if I need to keep breaking this down into factors, I can use q, r, and s. I shouldn't have used k after n. I should have used p, but whatever. So then c must contain 3, 6, 9, all the way up to 6p, which is the same as n. Okay. So C has a sum of at least 3 plus 6 plus 9 plus all the way up to, I'm going to not write 6p, I'm going to write 3 times 2p. Okay? The reason I'm going to do that is because now I can write it like this. The sum of C has to be greater than this. Okay? And so that's 3 times 2p plus 1 all over 2. These 2's are going to cancel out. So that's 3p, 2p plus 1. Okay. Now 3p happens to be k. So we're looking at k times 2p plus 1. And if we compare that to, what does the sum of C have to be? It's got to be k times 2k plus 1 all over 3. Okay. Divide both sides by k. We're left with this. I don't know whether or not to put a greater than or less than sign or what in there. Okay, multiply by 3. So let's write it like this. So notice that n plus 3 is greater than n plus 1. But of course, n plus 3 is 6p plus 3, and n plus 1 is 2k plus 1. You divide by 3 on this side, we'll be left with 2p plus 1 must be greater than 2k plus 1 over 3, and now multiplying by k on both sides. So this is the minimum sum of C, and this is what C must add to. So C already has too many elements. Or not necessarily too many elements, but they add up to too much. So 3 can't divide k. Therefore, 3 must divide 2k plus 1. Okay. So 3's got to divide 2k plus 1, which of course is n plus 1. Now what can I do? So let's let n plus 1 equal 3q. Is this enough to prove it? What do we want? We want n plus 4 over 12, right? That's what we're looking for here. So it needs to look like 12r plus 4, something like that. Let's add 3 to both sides. Okay, so then we need to know that this is a multiple of 12. It's got to be a multiple of 6. N is even, so we can write, we can instead say 2k plus 4 is equal to 3q plus 1. That's great. And so to get a factor of 2 here, so we've got that. Therefore, 3 divides k plus 2. I don't know if we'll need that. And 2 divides q plus 1. So q's got to be odd. We're not done yet. Because what we need to show is that 4 divides q plus 1, because then this thing on the other side will be a multiple of 12, and so n plus 4 will be a multiple of 12, n plus 4 divided by 12 will be an integer. So we need to show... So we need this. What we've got right now is that 2 divides q plus 1. So it's not enough for q to be odd. We need to know that its remainder is 3 when we divide it by 4. Okay. Suppose q looks like 4r plus 1. Okay? This isn't what we want, so we're going to try and show that this can't happen. I don't know how yet, but we're going to try and show that this can't happen. Maybe it has something to do with a being even, or the sum of a having to be even. I don't know yet. Yeah, so n plus 1 is 3 times q. That's 12r plus 3. So n is 12r plus 2. Okay, still not quite sure how this is helping us, but we'll do it. 2 times 6r plus 1. So no, I don't need to do any of this. I think a having to be even is enough. Yeah. So since b only has even numbers, it must have an even sum. Okay. Therefore, 2 must divide n times n plus 1 all over 2. But n is even. So n plus 1 is odd. Okay. So 2 must divide, and we said we could write it as 2k. Divided by 2, cancel that out. 2's got to divide k times n plus 1, but 2 can't divide n plus 1 because it's odd, as we just noted. Therefore, 2 must divide k, and let k equal 2r. Therefore, n is 2k, which is therefore 4r. So n plus 4, which is 3 times q plus 1, we can rewrite this as 4r plus 4, 3q plus 1. And so 4 times q plus 1, 3. Now 4 can't in any way divide 3. 2 doesn't even divide 3. So 4 must divide q plus 1. Therefore, let q plus 1 equal 4s. So n plus 4 must be 3 times 4s, which is 12s. So that must be s, which is an integer. Yay! Okay, so that was a lot of factoring and chasing that stuff around. We had a proof by contradiction in here. We said, what if n was the multiple of 3, and then it turns out there's too many multiples of 3. C was larger than the sum it would have to be, and then B has to have an even sum. They all have to have an even sum. So 2's got to divide this, n times n plus 1 over 2, and from there we can conclude that n's got to not only be a multiple of 2, but a multiple of 4. And then from there we were able to work out a multiple of 12. Okay, so that's great. Now C was determine all even savage integers less than 100. Fine. Thanks to B. So by part B, we still haven't used really the fact that A has to have an even number of odd numbers in it. Maybe that'll come up here. But that's a sort of a consequence for A having to have an even sum, which we've noted, because B has to have an even sum. By part B, we only need to consider numbers less than 100 with n plus 4 over 12 being an integer. So n could be 8, 20, because 20 plus 4 is 24, 32, what else can we have? 48 minus 4, so 44, 56, just keep adding 12 each time, 68, 80, and 92, and that's it. This isn't our list, but these are our candidates. Okay. So we already know 8 is savage. Great. So now we have sort of a question upon us. Do we think that this list is short enough that we can just go, is 20 savage and do it the same way we did part A, and then is 32 savage and do it the same way we did part A? Or do we think this list is too long and that this will be too exhausting and too much guess and check? Should we continue to investigate savage numbers and see if we can find an even better pattern than n plus 4 over 12? Okay. Now, I'm inclined to believe that we shouldn't trust either one of those, and we should start going through the list as though these are all as easy as part A. Try 20 and quickly show if is 20 savage or not. And then if we notice that certain numbers aren't being savage or that it's taking too long, see what patterns we've been able to come up with completing as much of the list as we already have. Okay? But I think with 20, 3, 4, 5, 6, 7 numbers left to go, we should probably just be able to try them all. I think if there were a better property, they probably would have asked us to prove it in part B. Okay? So let's try 20. So with 20, C is going to look like 3. First of all, what's our sum? Sum of each set is 20 times 20 plus 1 all over 2 and then divided by 3 again, so all over 6. So this is 20 times 21 over 6. 3 will cancel out with that, so that'll be a 7, and then 2 will cancel out there, so it should be 70. 70 is the sum of each of those? Alright. So C is going to look like 3, 6, 9, 12, 15, 18, and that's it. That's all we've got so far. And that's a sum of 9 plus another 9 is 18, plus another 18 is 36, plus 12 is 48, plus 15 is 58, plus 5 is 63. So the sum there is 63. Is there a quick way we can do these sums? It should be the next number 21 divided by 3. So it should be n plus 1 divided by 3 times no, 3 times, because this is 3, 1, 2, 3, 4, 5, 6. How do we know it's 6? Because the next one would be 21. So n plus 1 over 3 times n plus 1 over 3 plus 1 all over 2. That's that formula. Right? Yeah. Is there a faster way to calculate that? So the natural sum of C, the sum of the multiples of 3, is 3, as I say, 3 n plus 1 over 3. Oh, it's going to have to be minus 1, my mistake. Because it's this number plus 1, all over 2. This number times this number plus 1 over 2. So the 3's will cancel out. That's fine. We can turn this minus 1 into a 3 over 3. So that'd be n plus 1 times n minus 2 all over 6. Is that it? So 21 times 18 over 6. Let me just grab my calculator. 21 times 18 all over 6. 63. Okay. So that's fine. In this case, C has a sum of 63. We need 7 more. How can we make 7? We could have 1 and 6, for example. We could have, can't have 3 and 4. We could have 1, 2, and 4. That's a possibility. But with, we could have 5 and 2, for example. That would also do it. But I think those are the only possibilities. So, is taking the odd number, the even numbers will be, I think, naturally higher, maybe? I don't know. What's our sum of the odd numbers? Do we want the sum of the odd numbers, or do we want the sum of the even numbers? What do we want? Let's figure out the sum of the leftover odd numbers. So the odd numbers will be 1 plus 3 plus 5 plus 7 plus 9 plus all the way up to n minus 1, because remember n is even. And then we need to get rid of every third number. And remember, n plus 1 is a multiple of 3. So just going on groups of 3, it'll be these guys, and then n plus 1 will be left over. So this has a sum of 9. This has a sum of 27. We wouldn't have 3 to work with, we wouldn't have 9 to work with, and then at the end we'd also have a plus n minus 1. So that's 6, 18, it'll be 12, or add 12 again, so it'll be 30. Yeah, it's going up by 12s each time, right? So the next one will be 13, 15, 17, but we don't count the 15, so it'll be just 13 plus 17, which is 30. So it'll be 6 times 1 plus 3 plus 5 plus etc., and then plus n minus 1. Sum of a bunch of odd numbers is a square. Which square are we talking about? That's a good question. Which square are we talking about? Well, it's how many multiples of 3 we've got. So that'll be n minus 2 over 3. N minus 2 over 3. 2 times that plus 1. Right? So then it'll be n minus 2 over 3 squared. Let's check. Does this work with our formula with 8? 8 minus 2 is 6, over 3 is 2. Square that was 4. 6 times 4 is 24. Plus 7. No, something's gone wrong. We want to do that minus 1 there. So it would have been 6 times 1 for... We should get a 1 here for 8. So I think we're going to want minus 5. Okay. So this is the sum of the odd numbers, other than the multiples of 3. N minus 5 over 3, all squared, times 6, plus n minus 1. I don't think there's any simplifying that even further. Okay. And how about the even numbers? So the even numbers are 2 plus 4 plus 6, but we're not going to be counting the multiples of 3, plus 8 plus all the way up to n, which is an even number. And then n plus 2 isn't a multiple of 3, and then n plus 4 is, as we've already seen. So that means n minus 2 is a multiple of 3. That's fine. So these ones, then all the way up to this, then plus an n at the end. So 2 plus 4 plus 6 minus the 6. 8 plus 10 plus 12 minus the 12. So we've got 6. We've got 20. Then we would have 14 plus 16 plus 18 minus 16. So that would be a 30. Oh, sorry, this isn't a 20. It's an 18. So once again, we're going up by 12s. So I think do we have the exact same formula? Surely we don't have the same formula. just plus an n. We would have had 1 plus 5 plus 7, and then we would have had 2 plus 4 plus 8. Yeah, I guess that does work. What about for 20? 1 plus, not 3, 5, 7, not 9, 11, 13, not 15, 17, 19. And then we would have 2, 4, not 6, 8, 10, not 12, 14, 16, not 18, and then finally 20. That's a difference of 1, but then that counts as x. So those are the same. Those are the same sum. Those are the same sum. Yeah, it's just an extra number. Okay. So what does this tell us? Sum of odds minus the multiples of 3 is 1 less than the sum of evens minus the mults of 3. Okay, the multiples of 3 are already taken away. They're being used in C. That's fine. So to make A and B have same sum, the numbers we add to C that are odd must add to 1 less than even numbers we add to C. Okay? Because then we'll balance things out. Like when we took 1 out of the odd numbers, and then we took 2 out of the even numbers for 8. So this is probably an important thing to know. So now getting back to 20. So for 20, it default adds up to 36, so we're missing 7. And we could express that as we could have 1, 2, and 4, or we could have 2 and 5, or we could have 1 and not 6. I thought I had another one listed as a possibility. Nope, 1 and 6, I was mistaken. That one wouldn't work at all. So none of these possibilities work. The only thing we can do is take out 1, 2, and 4, or 5 and 2, and these don't work. And you can see I'm sort of arranging it as a chart. So I'll have the n that we're considering, the natural sum of C, which I just had a formula for that. N plus 1 times n minus 2 over 6. What is needed? So that'll be this sum minus the n times n plus 1 over 6. And that'll always be difference between those two is going to be 2 over 6. That doesn't seem right. Something's wrong. And then the possibilities that we need to work out. That'll always be n minus 2 over 6. So that'll always be 2n plus 1 all over 6. So in the case of 20, it was 21 times 2 all over 6. The 2's cancel out. And it'll always be n plus 1 over 3. Oh, that's nifty. That's always what we need. So actually, we could probably just make n plus 1, and the possible ways to express it where the even numbers add up to one more than odd numbers. Okay? And if there are no ways to do it, then this thing fails. So 20, we needed 7, and we could do 1, 2, and 4, but that doesn't work. Or we could do 2 and 5, that also doesn't work. How about 32? What else do we need? 32 plus 1 is 33, divided by 3. We would be missing out on 11. So we'd put all the multiples of 3 into C, and we'd be coming up 11 short of that sum that we need. So are there ways to write 11 as a sum of some even numbers and some odd numbers, so that the odd numbers add up to 1 less than the even numbers? That's the idea. That's what we need here. So we can have 5 and 6, but that doesn't work. Why? Because 6 is a multiple of 3, so it's out. We could have 5, 2, and 4, and that works. So 32 is savage. Great. Okay, now the next one, 44. We'd be missing out on 15 of them. Can we write this as, well, yeah, 7 and 8 would work just fine. Neither of those is a multiple of 3, so 8 can be removed from the list of even numbers, 7 can be removed from the list of odd numbers. So 44 is savage. How about 56? What are we missing? 56 plus 1 is 57. And we divide that by 3, we get 19. This is going up by 4s each time, so the next one will be 23, and then 27. Can we write 19? We would want to do something like 9 and 10, but that wouldn't work. Where's my eraser gone? There we go. Okay. 9 and 10 would be nice, but that's not gonna. I mean, the odds need to add up to 9, and the evens need to add up to 10. So 10's fine. It's just, can we find a way to add some odds up to 9? Well, we need 2 of them aren't going to work. We need at least 3 of them. And 1 plus 5 plus 7, that's going to work. There's no way to do this. We'd have to have something like 1, 3, 5, 7. There's no way we can get 9 out of here. Because 9's not allowed to take out, because 9's already in C. 3, you can't do it, and there's no way to add 1, 5, and 7 to make 9. So 56 is out. It's not savage. Our next number, we had 12, so we get 68, and then we'll have 80, and then we'll have 92, and then we'll finally be done this question. 33 here. No, not 33, 31. Uh, 23. The odd numbers need to add up to, well, the evens need to be 12, and the odds need to be 11. Oh, it's going up by 2s each time. Okay. 12 could be done with 4 and 8, and 11 could be done with 11. So that works out nicely. How about 27? We'd need to have 13 and 14, and both of those work out fine. So I'm noticing a pattern. It goes 2, then not, then 2, then not, then 2, then not. So I think to be savage, we probably need n plus 4 must be a multiple of 36, something like that. No, not quite that, because 8 doesn't satisfy that. So maybe something like n plus 28 must be a multiple of 36. Or no, must not be a multiple of 36. That's what we're looking for. There, I think that'll do. No, because n plus 4, whatever. Not going to worry about this right now. How about 31? We would need 16 and 15. So 16's fine as it is. 15, that's a multiple of 3. Can we make it with just using odd numbers and none of them being multiples of 3? 1, 3, and 11 won't work. 1, 5, and 9 won't work. 3, 5, and 7. Let's see. 1, 3, 5, 7, 9, 11, 13. So the 13's out because we need to at least add 2 to it, so that's not going to do anything. 3 and 9 are out. 5, we would need to be able to make 10. We can't. 7, we'd need to be able to make 8. We can't. This one just won't work. Okay. So yeah, it looks like every third one won't do the trick. So not that expression, but maybe so 32 did work, so it's plus 16 is what we don't want. So n plus 4 over 12 is an integer, but n plus 16 over 36 is not an integer. I think that would do it. Okay? I think that's my guess. I don't know. I don't have a proof for this, but that would be my ultimate guess as to what makes savage numbers savage. But we can finally say 8, 32, 44, 68, 80 are the savage numbers. Less than 100. Okay? And I admit the chart could probably use a little more explanation, but I think it's pretty clear what's been going on, especially based on some of the work we've done. And we're able to narrow down our calculations a little more. But yeah, that certainly took a lot out of me, and that took a while. I liked A and B part. C part, maybe there was a nicer way to approach B that made C a little easier and made these calculations a little more obvious, but A was a challenge, and that's what you should get with question number 10. So there it is. That is the Euclid. We're done the 2003 Euclid. Give yourselves a round of applause, even if you just attempted 10, whether or not you actually got it. Still quite a challenge to do the scholarship paper. So what's next? We're done the 2003 Euclid, so I guess we look now for the 2004. That's the next year contest. So Gauss 7? Gauss 7, anyone? I'll see you guys, whatever ends up being the next video you watch of mine. I'll see you there, and thanks for watching.